Now that we know these glacier systems are changing, one of the really pressing questions is how much, how fast. We want to be able to project future sea level rise. It turns out in order to do that, we have to really come to terms with the fact that glaciers are non-linear systems. Sometimes you push them a little, they respond a little. Sometimes you push them a little, they respond a lot. And there are two really interesting and potentially very damaging processes that might play out in West Antarctica that will lead to accelerated mass loss through time. So to really accurately project future sea level rise, we need to better understand these instabilities in the system that we call the marine ice sheet instability and this potential hypothesized marine ice cliff instability. This plot here on this slide is the projected mean sea level rise from the IPCC's AR6 report, our most recent State of the Climate report. My kitty really wants to talk about them. You need to go away for now. See you, Cinder. What you can see here is a distribution of projected future sea level rise. Those curves labeled SSP, those are different emission scenarios. They're called the shared socioeconomic pathways. They're the UN's predictions about potential human behavior, from very optimistic carbon reduction scenarios to very pessimistic burn it all style scenarios. What you can see is that there's this broad distribution of possible futures, just from future behavior. Those futures incorporate this process, our understanding of this process called the marine ice sheet instability, which leads to accelerating ice loss through time. You can see there are also these dotted lines that are at the very high end. Those represent futures in which we burn a lot of fossil fuels, but also this other unstable process, the marine ice cliff instability process, takes over. In order to kind of understand uncertainty in our high-end projections, we need to think a lot about these two processes. So I've mentioned before that the West Antarctic ice sheet sits in this deep bowl in West Antarctica. It's a marine ice sheet, which means it sits on the sea floor. And it turns out that in the early 20th century, we came to terms with the fact that ice sheets that sit in these deep bowls, these deep marine bowls, are geometrically unstable. And we can think through mathematically why that might be the case. So plotted on the right here, I have two example glacier cross sections. You can think about like this axis as distance, this is elevation, the y-axis is elevation, and the gray arrow represents the ice flow direction. As we talked about before, in glacier systems we have this general rule that the strain rate is proportional to the stress to the third power. Remember that driving stress is rho g h sine alpha, where h is the ice thickness. That means that the rate at which ice deforms is about thickness to the third power, scales with the thickness to the third power. We talked about how ice flow, if we have a stack of boxes, ice flow is the integrated deformation in all of those boxes. So if we think about integrating the deformation with respect to the thickness, then we might expect that the velocity of a glacier system scales something like thickness to the fourth. The stress was thickness to the third, we integrate that, we go to thickness to the fourth. So if we think about the amount of ice that's discharging out of the glacier system, which we can also calculate as if it were the speed of the glacier times the thickness of the glacier, we might expect that the amount of ice that flows out of a glacier system scales with thickness to the fifth power. That's a really strong nonlinear dependence. So let's imagine a glacier that's in equilibrium. To say it's in equilibrium or is in steady state is to say that its inputs equal its outputs. So we just said that its outputs scale with something like thickness to the fifth power. Inputs, instead, are simply the accumulation rate of snow, which we'll call B, times the area over which accumulation is deposited. which is a function of the length of the glacier and the width of the glacier. Length times width gets you area. Okay, so we've seen the fact that in a glacier system, the output scale something like h to the fifth, the input scale something like the area times the accumulation rate. Imagine we have a system that's happy, outputs equal inputs, and then we perturb it by doing something like melting off the end of that glacier. So if we melt off the end of that top glacier, the thickness goes down because we're retreating up a slope. We're retreating into an area where the ice was thinner in this geometry. The thickness goes down, and the area receiving snow goes down because the length of the glacier has decreased. In this case, because the outputs scale with thickness to the fifth power, that means the outputs drop by a ton when we go into that thinner ice. Meanwhile, the inputs don't go down by nearly as much. They also go down, but they scale linearly with the area. So now our outputs have gone out by a ton, our inputs have gone out by a little. The system is out of balance, but it's out of balance in a way where the inputs exceed the outputs. So we would expect this glacier system to grow. So it's likely the case that this glacier will re-advance until it returns to that state where it was in equilibrium before. What happens if we look at that glacier system on the bottom? It starts out in equilibrium, outputs and inputs equal, and we perturb it. Now, we've perturbed it into a region where the thickness is greater. Because the outputs scale h to the fifth, we have a situation where we're in thicker ice and the outputs have gone up, and they've gone up by a lot because it scales thickness to the fifth power. Meanwhile, the inputs have gone down. This system is now out of balance, but it's out of balance in a way where the outputs exceed the inputs. That means we're going to discharge even more ice out to the ocean, and the system is going to shrink. This leads to an unstable positive feedback loop that we call the marine ice sheet instability, where ice sheets that sit in these deep, over-deepened bowls, if they start to retreat, they tend to retreat catastrophically. So our understanding is that when we start to deglaciate West Antarctica, the West Antarctic ice sheet, it's going to accelerate and accelerate and accelerate until the West Antarctic ice sheet is gone. So if we want to understand the future rates of sea level rise, we really need to understand how this positive feedback works and how quickly it will start to dominate the system. We're already starting to see a retreat from Thwaites and Pine Island Glacier that we think indicates the action of this marine ice sheet instability has begun. The other question we have to answer is what processes other than ice flow might start to take over in a system that's in rapid retreat. One thing to take note of is that ice shelves apply a back stress to glaciers, to marine ice sheets, to glaciers in West Antarctica. We talk about that stress using the word buttressing. This image right here is Notre Dame Cathedral, and these are the famous flying buttresses in Notre Dame Cathedral. Anytime you have a steep vertical face of any material, gravity wants to pull that thing down. Gravity wants to break things that are steep and vertical. If the gravitational force is high enough, that stress can break it and those walls would collapse. To prevent that from happening, at Notre Dame, they build these flying buttresses to hold up the walls. Well, glaciers can also have steep terminal faces. Right now, those are buttressed by ice shelves. But in a warming world, it's possible that surface melt will lead to the breakup and disintegration of ice shelves, and what we'll be left with is a cliff at the edge of the ice sheets. If that happens, when we have quite thick ice, imagine here is our ice sheet, and here's the water line. Let's say we're grounded. There's rock down here. If we think about the stresses in this system, in the ice sheet, pressure increases as we go down. And so there's a stress pushing on this face that increases as we go down. In the water, too, pressure increases as we go down. So the water is applying some backstress to this system. But right at the water line, right here, there's a very strong stress being applied by the glacier that isn't restrained by anything. If it's the case that that stress exceeds the strength of ice, the fracture toughness of ice, then what might happen is that this ice is going to break off in a big tabular iceberg. There is no rate limit to these brittle processes. They could happen catastrophically fast. And so there's an open question. If we retreat into the deep interior basins of West Antarctica, will this marine ice cliff instability take over and lead to the rapid unstable collapse on decadal timescales instead of century timescales? So, to understand the future of the Antarctic ice sheet, we really need to think about these two unstable mechanisms that exist for marine ice sheets.